Okay, so I think it's time to start the panel discussion. So if we can bring everyone into the panelist mode, and we can probably see everyone coming up. Okay, great. Thank you very much, everyone, for keeping your time for the for your presentation and have this discussion time afterwards. So one of the things I tried to see the common denominator of all the different, diverse research projects you have presented so far, and it's actually difficult to find, right? It's so different and so diverse, but at the same time, I think I see dynamics, like dynamic aspects of embodiment, like all the bodies that we're dealing with is not the sculpture, is not passive, but it's active and changing its own shape, but also it's the structures. And that's one of the key aspects we discussed yesterday about the morphology, changing morphology as the new tools to understand embodied intelligence, and that's one aspect of it. And the second aspect of it is the contact, the physical contact between machine and the environment, or with human bodies. Is actually a holy grail. It's a grand challenge, like how we can make machines more actively, more sensibly touching to the physical environment. So I think these are 2 points I just want to raise as kind of discussion topics with you. I don't know, anyone want to chip in any ideas from this point of view? I think I see Jamie want to speak something, so I hand over to you and say, start the discussion from there.
Sure. So I guess I can be a little more narrow, because in terms of the wearables, that's one of the biggest trouble or challenges that's facing us. And it's very difficult to define what it means by comfortable. So I know Professor just presented his work, and that's just mind blowing, because it's something that I've been following closely. But other than, I guess I'm actually asking more questions. I know in order for me, I realize grounding is very important to actually evaluate the performance of any type of wearable robots. We understand that robots that are interacting closely, physically closely with humans, need to really match not only the actual point of the rotation or the radius of curvature in terms of where they're attached, but as well as that when they need to be or shared autonomy of when it needs to be actuated or not be passive, but understanding how far is too much, how much of autonomy should be given to the robot, and under which circumstances. Well, it's so easy to test them on a test bed, so easy with a quotation, but it's a completely another thing once it's on a human subject. That if it's a human subject changes their big, not necessarily biomechanics, but just pure dimension, or how it's actually dawned on, it changes the complete performance profile. So for in my lab, we were trying to create a more consistent way of measuring this, even on a desktop. And then creating different types of environment to induce if it were to be grounded in different fashion. So those are a couple of efforts that we're trying to do in the lab. I'm just wondering if the extra small HAL robot on the small kit, how that was experimented previously to being dawned on. I'm very curious to hear what you have to share with us.
Yes, Yoshiyuki, do you think you can give us a bit of comment about how you thought of what Jamie called grounding, right? I think grounding has multiple meanings, but
that's true. That's true, right?
Yes, and I think that's an interesting way how robot can actually accept it by users, or robot adapt to the users, and how robot and humans make impact together. I think that's the kind of interesting point that you're presenting. Yoshiyuki, do you have any comments you want to give?
Oh, yes. Thank you so much. Thank you. Yes. So anyway, I think so. In my cases, target is every patient has a different situations, and during the treatment, patient even the same patient situations gradually changes.
Mm, mhm.
Okay. So during the 10 minutes and 20 minutes,
That's
30
right.
minutes. Okay. So at that time, so interactive feedback is very important to adjust the parameters and so on. Then I was very surprised. In the beginning stages, I tried to prepare some programs to estimate the few human situations, but the system is non-linear systems. And so
They all are.
everything
They're all linear.
very, very, very difficult. So I prepared some of the performance index and or some of the target as evaluation point. Then by using such kind of interactions, so automatically these systems adjust the patient's conditions. Then the patients can feel the natural feelings because if I prepare my uh, my my consideration programs, then maybe the patient feels bad, I think. But
Mhm.
anyway, most important thing is that in my cases, I always obtain the humans informations,
Right,
and I an I analyze these so many data
right,
informations real timely, and I changes the some only main part. That one is the one of the success, I think. So
mhm,
and after these processes, maybe I can analyze the more precisely, I think. Yes.
right. So just to add a little, I'll take prerogative of having my microphone on. So what are the informations that you're gathering from the patient to update your program?
Okay. Yes. One is the bioelectrical signals from the brain system, from the brain. Okay. Then maybe the 24 sensors attached uh, on uh, on their bodies and so on. But this one, the matrix type, is an easier way to use. Okay, and of course the heart functions
Mhm.
and movements meaning the this system is very interesting. To obtain the patient's data, we can only analyze the heart system's data because the movements completely synchronized with the humans and these systems. Then it's an easier way to obtain the humans' movements and acceleration and speed and contact part because this system has a special shoes to
Mhm.
detect the reactions between the soul and
Right.
uh,
The
proas.
ground
Yes,
reaction force, right? Yeah.
yes, yes, that's right. Yes,
Mhm.
yes. And so recently we start to create another challenges uh, with the psychologist. So
Oh, wow. Yeah.
yes, from the mental information also, this one is not so quick, but slowly we try to
Right.
establish a feedback systems by
Right.
using the mental issues and so on.
Right.
Yes,
But what you said is the simultaneous feedback comes from the EEG signals as well as the ground reaction force from
that's
the
right.
patient
Yes,
easily. Okay.
yes. But easy cases, wow. So, mm, okay. So, easy case. So, strong persons or the weak persons signals is a little bit different.
Okay.
Then, so we have maybe the biological signal is very nice because so very small, but we can please separate these signals even in the EEZ and EMZ and so on. Yeah.
Right. Thank
Yes.
you.
Yeah.
Okay, thank you for the very interesting insights into this system, a very complex system, actually. Any other points other panelists want to raise? Um, So one of the things I probably want to ask Helmut is probably, this aspects of physical and informational interface of embodied intelligence as, the Yoshiyuki talking about physical motion as well as gaining real-time data from a human biometabolism and so on. I think this is one of the real challenge, how we can think of embodied intelligence in the context of putting physical process and the informational dynamics. And you talk about dynamic intelligence, dynamic embodiment. Do you have any views how we could start thinking about this this two traditionally separated world?
Yes. So I think the dynamics are at different levels, right? And very often, at least in my mind, I compare like biological system and how embodiment works there, and then try and transfer it into robotic systems. Now, the problem is humans is we are very complex systems, and even very simple biological systems are very complex. So we have to find stepping stones into this direction, right? I think eventually we'll have to have growing machines to realize that in physical systems. But I think by starting at what Jamie pointed out, right, increasing degrees of freedom, I think that it's beautifully put, that you open a space there, right, of having more possibilities. I like her idea a lot there. So that's one way to go, and also having more kind of degrees of freedom that are more decentralized, acting in a passive way, that they're like the stimulation that comes from the outside, or different types of stimuli comes to the body, can be actually translated into some changes without talking to the brain of the machine and robot. So these are these smaller stepping stones. I think it's really hard to do, right? We need material science, we need biohybrid approaches there. We need maybe completely organic robots, so we can take advantage of already existing mechanisms in biological systems to implement that. But there are a lot of different directions we can go and we should explore. It's a very complex topic, I agree.
Yes, absolutely. I was just realizing that the Jamie is talking about impedance matching as one of the challenging topic for the human wearable devices and so on. The impedance matching is such a deep conceptual problems, I think, to understand how information dynamics and physical dynamics come together. And that was probably related to what Jamie means by grounding of the wearable systems, and obviously impedance matching is the key to really solve the physical contact, physical interactions with complex environments. I don't know whether Kyujin or Lee want to chip in something from your experience or your research project, how you deal with physical interactions. You specifically work on the contacts, right? You're working on. So Kyujin, you want to chip in something?
Yes. So I think if we look at our human body, when we build robots, we focus on creating actuators, attaching actuators to create motion. But actually humans have a lot of tendons as well. And those actually affect the impedance. And if you can change those impedances artificially, then that means we can actually change the energy barrier. So even with like a simple actuation, or even without actuation, humans' behavior will be affected by the change of the impedance surrounding the body. So I think a little bit related and could be a different point, but I think we should try to make use of those kind of artificial and like impedance changing, variable impedance changing if we can. And then add actuation on top of that. So that way we can actually do like that kind of impedance matching if needed.
Is there any discussion about what are the ground the most difficult challenges to achieve impedance matching? Like what's the fundamental problem? Like is it actuators, or is it a transmission, inertia, or mechanical design, or control bandwidth?
そうね。そうね。Okay. So, hello. So, in my case, so during the walking, so patients always had a contact on the ground. Then every steps, so impedance should be controlled. Then this one is very important. So one is the actuators realize this impedance controls, and also soft tissue is also very important. Yes. So these combinations very important, I think, in my case. Okay.
Oh, that sounds like a real problem. If you have a soft tissue and high impedance control bandwidth, then yeah, that sounds like already a very challenging problem.
Can I ask Professor Sakai something? So, I mean, do you actually do something do you change the design, or like vary some length or something because different people have different impedance.
Yeah.
Match that. Do you do it by applying different control scheme, or is there some things that you do to actually more customize it to each person?
Okay. Yes, of course. For examples now, so this device is now used for the children. Okay, so children is always growing up. Then the size always should be changed. Then only one device, the size can be changed from the 100 centimeter to 150 centimeters. Okay, yes, and of course dynamic systems also gradually change. Then so impedance control systems should be adjusted by estimate the patient's physical parameters and so on. Okay, then this one is the principal setup, I think. Yes. And of course, the patient's muscle condition is completely different. Some of the patient muscle condition is very stiff. Some of the person is not so stiff. For example, cerebral palsy patient cases, they have a very strong muscle powers, but it's very not so soft. Even the humans, they are very strong, very stiff. Then these systems real timely should change the parameters, yes, to change the impedance and so on.
Okay, Helmut, do you want to comment?
Yes. Thank you. I would like to add something. I think what grounding also is basically like this tight coupling, right, between the agent and the environment. And I mean, one way is as a designer, you think about how can I design a robot so the coupling is better. That's one way to do it. But there is also another level when you look at biological systems through the evolutionary process. This tight coupling has been improved over time. So maybe we could also explore that in robots. And that's what I meant when I talked about having the potential as solutions in the morphology. So there's a way to adapt. We don't know the solution per hand, but we expose the robot to a certain environment, to a certain task, and then with these adaptive mechanisms, a solution emerges. So this is really hard to do, obviously, but I think there's a lot of potential in there.
Yeah. So can I comment a little bit more based on that? So I think, yeah, for example, the structure to modulate impedance. So I think, for example, metamaterial, if you squeeze it, it can change the stiffness or even twisting. It can be, show some extraordinary or unique mechanical behavior. So I think adding a special structure, flexible structure, could be one interesting way to do the impedance matching. So for example, the metamaterial, which has been studied a lot recently by solid mechanics people. So I think they are very curious in how to apply the metamaterials into software robotics for many applications. I think impedance control, variable stiffness is definitely one important areas. So, yeah.
Yes, absolutely. I think materials plays very, very crucial role in order to achieve better impedance matching, because obviously there's no time delay, right? If you can do impedance matching in the material level. I think that's what biological system is doing in any way. So I think that's going to be the future of wearable robots. Jamie agrees.
Yes, but I hope, but I just want to point out that we also work with multiple materials, and that sort of adds a extra complexity. So if you have a single material with a single format, then maybe we can sort of pinpoint out the coupling, but the coupling gets a little more complex when you actually have multiple materials embedded in one after another in the different sections. And from the configuration of the interaction, that contact point changes, the depth of contact changes. So these are the additional complexity, I think, that throws off a bit as well. So I actually like how Helmut said that it's matter of coupling. I like that. But I guess next question is, how do you go further in making this coupling a little more not so time dependent, not so trajectory dependent, not so configuration dependent, or maybe they need to be. So that's just additional question that rises a bit.
Okay.
Maybe also in addition, if I might, I would like to add also that we're talking about stiffness all the time, right? And I mean, most of us using compliance systems to a certain extent, right? Maybe soft robotics but I think coupling doesn't necessarily have to be done through stiffness, right? I think there's also other mechanical properties which are important, like dampening as well, but also chemically coupling, right? Especially if you talk at microscale robotic system, if you have chemotaxis, there's a coupling with the environment that is actually non-mechanical. So I think we should broaden the discussion here and
even further,
yeah, take it further. Yep.
Photocoupling.
Okay, so then I have just one last question, probably mostly to Yoshiyuki, about the social aspect of the whole thing, because the next plenary speaker, Hiroshi Ishiguro, going to talk about this. It's probably good to prepare for it a bit. That we have all the different kind of wearable systems around us, and obviously all these wearables will be connected through internet or whatever other means. And are these wearables going to shape our brain after all? Like, how are we going to deal with all these wearables with different perception or different ways to interact with the broader world than we used to know? Yoshiyuki, do you have any views or comments on this aspect?
Yeah, wow, very interesting. Yes, I think so. Body and skin is a part of brain, I think. Yes. So that one is my
That's true.
comments. Yes. So maybe by creating some kind of wearable device or some similar devices, maybe our brain and our total systems will be gradually changed, I think. Yes. Yeah. Especially skin is a part of the brain, I think. Yeah.
Do you think we should protect our brain from, the shaped unintentionally by wearable, or we just let it go? Is there any, circuit breaker we should think of, or we just don't care about this? Any comments? No?
Any comments?
It's open questions, I suppose.
Right? I think everything is connected. I think it's unavoidable.
I think
have
so.
to-
Yes, yes, that's right. That's right. Yes. Everything's connected. Yes, I think.
Yeah, so we have a very interesting discussion in the first day about the network problem, like a network aspect of brain, and our brain is really good at networking in homogeneous or heterogeneous ways, and I think those are the key aspects how we understand our brain activities and dynamics, and this will be probably connected to our physical networks, and that's going to be the next interesting challenge, and hopefully we will understand better understanding of embodied intelligence by this new devices, new technologies that we can use for our research, and the wearable is actually playing a very, very important role, I think, in this context. Okay, I think we're going to close this session at this point. Thank you very much, all of you, and we'll probably ask you to come back later for the final summary discussion after the next plenary talk. So thank you very much once again. Wonderful lectures and the discussion. Yeah. So we will have a 30 minutes break before the next plenary talk by Hiroshi Ishiguro, and we'll see you again at 11 a.m. GMT. And until then, we'll see you later. Thank you.
Thank you. Bye.
Thank you.